Okay, so last time we have described how to derive the wave equation in free space. In free space, it's very important. It means that there is no charge in the space, and also there is no current, no matter the static current or the displacement current in the space. So it is called free space, which means that the EM wave can propagate in the space freely. Okay, so now let's talk about the how to solve the wave equation in one dimension, which means that the second partial derivative of the E field with respect to x equals 1 over c squared, which is the speed of light squared, and times the second partial derivative of the E field with respect to time. So on the left side, this is related to the change in space, and this on the right side it is related to the E field changes with respect to time. Of course, this is the second derivative, not actually the changes. Yeah, it is the change of the E field. Yeah. So so this is the so-called the partial differential equation. Generally, partial differential equation is difficult to solve, but some types of PDE, so-called partial differential equation, in short form it is PDE. Some types of the PDE will be easy to solve, and of course you can also try to use this so-called the separable of variable to solve the PDE. Some will work, some will not work. If it works, then you can come up with a solution quickly. If it doesn't work, then probably you need a more difficult way to solve. Something like you need to take the Fourier transform of the PDE and then solve it in the frequency domain, something like that. Or using the infinite series method, maybe you substitute some infinite series and then try to see the coefficient of it. But yeah, some types of PDE is not really possible to solve it analytically, and you possibly need to write a computer program to find a solution in a numerical way. Okay, so here the wave equation in free space is easy to solve. You can use the separable of variable to solve it. So of course here the E field is a function of the x and time, x and t, which means the position and also the time. So the point for the separable of variables means that if it is a function consists of multiple variables, then you try to assume that this function can be separated into two functions multiplied together. This function only consists of x. This function only consists of time. So that this is so-called the function is separable. And we try to plug in this one into the original function equation. You can really simplify it. Okay, so let's do this. Let's plug this one into the equation we'd like to solve. So this is the blue term, this is the green term, and then you plug it here. We have this one taking the second derivative with respect to x, and then plug in here, take the second derivative with respect to time. Okay, so this is a function of time which is independent to x. So we can just put this one in the front. We don't really need the product rule, because usually if you need to take derivative, something like, okay, I think I need to make it thick. How to make it thick? Oh, this is too thin. Okay. This is how to here, too thick. This is Okay, so usually when you try to take the derivative of a function like dx and then f of x, g of x, you need to use the product rule, which is like df dx times function of g plus dg dx times f. This is the product rule in the calculus. But here, this is independent of it, so which is like if you need to take partial et, partial second partial derivative. Actually, second partial derivative will be even more complicated, which is like a 1-to-1, something like that. Okay, so if you really need to take the first derivative, this is a function of time, this is function of this is x. So technically the partial derivative will be nothing but 0. So or you can just regard it as is a constant to the x. So which is like a factor, so you can just put it out. Similar on the right hand side, this is a function of x which is independent to t, so you can just put it out like this. Okay, so we have done a very important step, although it looks very simple. And then the second step is that we can move this term to the left side and then move this term to the right side, which means for this equation we can divide it by ex of x times et of t. Divide the whole term on both sides, which means that et and et will cancel each other, ex and ex will cancel each other. So finally, on the left side we have the second derivative of ex over ex. And then on the right side, this term and this term is cancelled. So we have this second derivative of et divided by et, also c squared here. So this is the punchline of the separable of variable of separable of variables, which means that originally you assume the function can be separable for different variables, for different independent variable, and then finally you get some equation which has also the separable of variable properties, which means that on the left side we only have x on the left side, and then we only have t on the right side. We don't mix the x and t on the left side. So in this case, this is a big function of x, a function of x. Maybe we can say this is like f of x. And then this is another function, g of t. They equals each other, which means that they must be a constant to make them equal to each other, because if x is fixed, t is changing, then this value doesn't change because t and x are independent to each other. So if t change, it must keep the value so that it can be equal to f of x, and so as the f of x. If you just keep t to be a constant, then if you vary x, then this value should still be a constant to make both sides equal to each other, which means that they should be equal to a constant. Let us call it a, small a. So next we get two independent differential equation, and actually here from here to here, from here to here, I use the partial derivative sign, and then here we use the ordinary differential sign, because this is nothing but a single variable function, so we can use the ordinary differential here. Okay, so we have two independent or two joint ordinary differential equation. This is the point of a separable variable, so we separate the function of x and t into two ODE. Okay, so let's try to solve these two equations. Actually, they are quite similar to each other. The only difference is that we have a constant c squared here. Can you use a thicker one? Okay, so here we can just move these two terms to the right side. To the right side, so it looks like the ODE constant coefficient ODE. So this is the second derivative. This is the original function. Okay, so let's see. We have three cases, or for the constant coefficient, just say this one. Just say this one. Okay, this one. If you try to solve it using the constant coefficient way, then this is the second derivative, so you change it to s squared equals a times 1, because this is the original function. So which means that s squared equals a. So there will be three cases. If a is positive, if a is 0, if a is negative. So let's consider it one by one. So the first one is a is larger than 0. A is larger than 0, which means that s squared equals a, and then we will have a s equals to plus or minus square root of a. Plus or minus square root of a, which means that the solution to it will be exponential to st. Ex equals exponential to sx, because it is a function of x, so it is not t, so it should be x here. So s is plus or minus square root of a, so e to square root of ax, like this, and then negative square root of ax. So we have these two solution, which means that the linear combination of it will be the solution. Okay, in this sense, similarly, we can also solve for this one. This one is only a little bit different, which means that if we change it to the characteristic polynomial, which is s squared, this is the second derivative, so it is s squared. And then on the right side, we have ac squared, which means that if we try to solve this one, a is positive, then s should be plus or minus c times square root of a, like this. So et will have the solution e to the square root of act, because this is a function of time, and then negative square root of act here. Okay, in this case, we have the solution. E of xt will be ex of x times et of t, which means that this part correspond to this part, which is the linear combination of these two functions. So we have a times exponential to square root of x plus b times exponential to negative square root of ax. And then for et of t, which is the linear combination of these two, so we have c times this one plus d times this one. Actually, this is not a good solution. We are not looking for this one because for this one, if a is infinitely far away, then this one will be infinitely large. Either x is a positive infinity or negative infinity. Either this one or this one. If x tends to plus or minus infinity, then these two functions will diverge. E will diverge. This is not the case we are finding, because if you still remember, for the E field we need the power. If the E field is infinitely large, which means that we need infinite power to generate this field, and this is what we are looking for. So this is not a good solution. So the next case is if a is 0. If a is 0, then the right side will be 0. The right side, this is 0. This is 0. So this is the second derivative equals to 0. So you integrate by 2 times. We have the linear function a plus bx c plus dt, and then the solution will look like this. Similar argument is that if x is positive or negative infinity, then this E field is also goes to infinity. So this is not good either. So finally, we come to the third case. The third case is that if a is smaller than 0, then we can try to rewrite it as a equals to negative of k squared, because k squared is always positive. So negative k squared is negative, or yeah, is negative. So we assume that k is a positive value. Yeah, actually, and yeah, so this one is always negative. Okay, so we can just plug this one back to here. So it equals to negative k squared ex of x. And then this one equals to negative k squared c squared et of t. Something like this. Okay, so when we try to solve this one here, the characteristic polynomial will be like s squared plus k squared equals 0. Or s squared equals to negative k squared, depends. So in this case, we have s equals to plus or minus jk. J is of course negative, square root of negative 1. Square root of negative 1. So s equals plus or minus jk. And for this one, we have s squared equals negative k squared c squared. So s will be plus or minus jkc, something like this. Okay, so actually for this one we have s equal to plus or minus jk, so which is complex solution, which means that we have the solution like this. Still I'm using I here. I is actually j. Okay, so exponential to ikx or jkx, exponential to negative ikx. Okay, so which is similar with it in segment system. So and also et of t. So we have, yeah, we originally should have jkct should be something like exponential to I, maybe I or I, kct. And here we will have kc equals omega. Omega equals kc, if you still remember. Because actually, if you still remember, k is the wave number. K is the wave number equals to, k is 2 pi over lambda. 2 pi over lambda. And then omega is 2 pi f. 2 pi f. When you substitute it into here, you will have 2 pi f equals 2 pi c over lambda. 2 pi and 2 pi can be cancelled, so we have f over c, f equals c over lambda, which is what we are similar to. C equals f lambda is the always true for the EM wave. And actually we also get this property, get this equation here. So actually we can just write kc equals omega. So it will look like exponential to I omega t. So it looks even more like the one you see in the signal system, although it should be j omega t. It should be j omega t if you have learned the Fourier transform. Yeah. Okay, so this is a solution for ex, and then this is a solution for et, and yeah, so of course here we have omega equals kc, and actually here we get this solution. Why it directly jump to here? Let me try to tell you. So originally we have ex equals, let's say a. This a is different from the a here. So I just use this variable exponential to jkx plus b exponential to negative jkx, and then maybe a b c d is not is not very good because c is is the speed of light. Maybe I use I don't know, alpha, beta, gamma, exponential to j omega t plus delta, yeah, negative j omega t. So if you just explain it, we will have alpha gamma, this one multiplied by this one, exponential to j kx plus omega t, and then plus this one multiplied by this one, alpha delta, exponential to j kx minus omega t, and then this one multiplied by this one, plus beta gamma, exponential to negative j kx negative omega t, and then finally this one multiplied by this one, and then we will have beta delta exponential to negative j kx plus omega t, like this. So we have these four terms, so maybe we can just replace this as a b, c, d, then we will get this expression. Okay, so actually these two are actually propagating in positive x direction, because we have kx minus omega t. This is negative kx minus omega t. So yeah, so you may ask why actually these two combined together will lead to a phase. So if you are familiar with the trigonometry property, then you know a times cosine plus b times sine of the same frequency, then it can be combined to something like a cosine omega t plus b sine omega t will be something like r cosine omega t minus phi or plus phi. It depends what you like. Something like this. So the combination of them will only lead to a phase, and then this one is propagated in the negative x-axis, because you can simply imagine if this is a constant, then if x is increasing, t is also increasing, which means it propagates in the positive x direction. This is positive, this is positive. So if t is if t is increasing, x should be increasing to keep this term constant. So this is propagating in negative x-axis. Okay, so we have all the four terms. Actually, we only consider this term because the EM wave should be a real function. That should be a real function. First, we only consider the one propagate in the positive x-axis, and we also try to make A is a complex conjugate of B, so that this will lead to a real function, and then there will be a phase there. But actually, if we pick a proper reference frame, then we can just ignore the phase there. So finally, we come up with this solution. If you still remember the Euler's identity, exponential to j omega t equals, or j kx minus omega t is actually cosine omega t plus j sine of omega t, if you still remember this one. And exponential to negative j omega t equals cosine omega t minus j sine omega t. So if you just add them together, this one and this one, then the complex one will cancel each other. We only have the real part remained with a single cosine there. So we have this 33.1 there, like this. Okay, so next We also try to solve for the magnetic field, so which is like you try to use this one is the let me see, this one is Faraday's law. Yeah, this one is Faraday's law. So if you consider the one-dimensional case, this one will be partial E partial x equals partial B partial t. If you just plug in this one on the left side, we will have partial B partial t equals negative partial E partial x, which is this one. And then this function, you can take the partial derivative with respect to x. So cosine will be negative sign, so cancel with this negative sign, so this become positive. And if you take the partial derivative with respect to x, you need to change rule. So it multiplied by k here, KEM sine of this one, like this. Okay, so then you can just take the integration of dt on both sides. So integration of dt. So dt cancel each other. So on the left side, we only have a bxt, and then on the right side, you take the derivative, you take the integration, and then integration of t. So sine will become negative cosine, but you still have the chain rule. This one you divided by negative omega. So this negative sign and this negative sign cancel each other. So it is still positive sign. And then we have k over omega here, k over omega, EM, and then sine become cosine, like this. So it goes back to cosine kx minus omega t, like the E field. And of course, this one is the BM we define. So we will also get the expression to be this term equals to Bm, k over omega times Em equals Bm. So if we just move over the term, we have Em over Bm here, and then on the right side we have omega over k. Omega over k is actually c, if you still remember. Omega equals kc, so omega over k is c. So we also get the expression 33.2 for the B field, and also 33.4, which is the amplitude ratio of the E field and B field in the EM wave, which is always a constant c. Okay, so here, this is the solution for the wave equation in one dimension. If we further generalize it in 3 dimensions, the solution will be only like k dot r. So wave number will be a 3 vector, and then also the position vector will also be a 3 vector. So they dot together become a scalar, like this. So in one dimension, the dot product is nothing but a multiplication, because they are parallel to each other. Okay, so r is the wave propagating direction, and then the k is the wave number vector. Actually, this is the GIF, but in PDF it cannot show. But actually, I think 2 weeks ago, I have shown a YouTube video. You already see the wave propagation there. And finally, I want to mention is that the energy density of the EM wave, because in the original slides, I've mentioned the pointing vector, which is the vector about the energy carried by the EM wave. So here, of course, we have this expression. The RMS value of the E field is the peak, the amplitude divided by square root of 2, and so as the magnetic field. And if you still remember, the energy density of the E field is 1/2 epsilon naught E squared in free space, and the energy density stored in the B field is 1/2 mu naught times B squared. So if you still remember, they are duality with each other. You change E to B, and then you change epsilon naught to 1 over mu naught. So we have these two expressions. And actually, in the EM wave, they should be equal to each other, which means that for the EM wave, half of the energy is stored in the E field and half of the energy is stored in the B field. So let's see, we have 1 over epsilon naught E squared, and then we know that the ratio between the E field and B field is nothing but E over B equals C, EM over BM, it doesn't matter. So E equals BC, so we have this term here, and then so we just distribute this square into C and B, so we have C squared B squared. And then if you still remember the speed of light, C equals 1 over square root of mu naught epsilon naught, like this. Okay, so we have C squared here, so we have a mu naught epsilon naught in the denominator. So epsilon naught and epsilon naught can be cancelled with each other. So we have, so it equals to 1 over 2 mu naught times B squared, which is the energy density of stored in the B field. So which means that the total energy stored in the EM field, half of it is UE, half of it is UB. So we have UE plus UB. And of course they are equal to each other. So we have 2 times of this term, which is epsilon naught E squared here. Okay, so the Poynting vector in the textbook, it tells you that the Poynting vector is E cross B over mu naught, and of course E and B are always perpendicular to each other. So E cross B will have the magnitude E times B over mu naught. So actually this one is actually equals to this one, because you can simply imagine this is the energy per volume, this is the energy per volume, this is the energy density, which is the energy per volume. So we have this one, and the Poynting vector is the energy per area per time. So which is like, originally we have the energy stored in this box, but actually the Poynting vector only consider the area per time. So we need to multiply. We need to multiply this length, and then also divide by the time. So actually this is the speed of light. This is the speed of light here. Between this one and this one, we need to multiply by the speed of light, because this area is the cross-section area. This is the direction of the Poynting vector. This is the direction. Actually, this one is parallel to this one. I don't join good enough. But anyway, we need to multiply by the speed of light so that we convert this energy density to be the Poynting vector. Okay, so we have C times this epsilon naught E squared. Okay, and actually, this one, C epsilon naught, let's see how to convert it. So we have E squared here. So E equals BC. So we have C times epsilon naught E squared. One of it changed to BC. So BC, like this. So we have C, so we have C squared. C squared is actually 1 over mu naught epsilon naught. So we have 1 over mu naught epsilon naught due to this one, and then multiplied by epsilon naught EB. And then this epsilon naught and this epsilon naught can cancel each other. So finally we get this EB over mu naught. That's why the Poynting vector is defined like this. Actually it is according to the solution to the wave equation. And actually, if you just see the history of the electromagnetism, then it will tell you that the Clerk Maxwell, discovered the Maxwell equation, and then he predict the existence of the EM wave. But of course, maybe like a few decades later, then Hertz really can measure the EM wave using an experiment. Okay, so this is the about the supplementary law of the EM wave.